So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Cotticcione. I'm the interim director of this afternoon. We have the great pleasure of having with us as a speaker Dr. Amartya Goswami, who's also one of the speakers of this month's mini school. And with him, we have Professor Zurab Yanelidze, who's the other speaker of this month's mini school on category theory. And Amartya kindly agreed to give us now a colloquium as a really an invitation to learn more about categories. Yeah, and since Zurab knows Amartya much better than I do, he kindly agreed to give us an introduction to introduce Amartya, and Zurab will also moderate the questions. So if you have questions, please make use of the Q&A facility or raise your hand, and Ilya and I will make a plan to give you the right to speak. So thank you very much. And Zurab, please, if you would like to introduce Amartya, you're most welcome.
Thank you very much, Francesco. Welcome, everyone. This is my great pleasure and honor to introduce Dr. Goswami. We know each other for a few years now, and it's an absolutely wonderful mathematical experience to interact with him. The novelty and braveness of his mathematical ideas are something quite unique. So at the moment he's working at the University of Johannesburg, and I don't want to say anything more because we look forward to hearing from Dr. Goswami directly. Please, Dr. Goswami.
Thank you so much, Zurab. Thank you very much, Francesco. It's a great honor and great pleasure for me to be associated with NITheCS. First of all, it's a very, very pleasant experience for actually Zurab and us to be part of NITheCS now, and also giving this colloquium and along with this series of talks for this October month. And we are very happy to be here. Okay, so what we are trying to do here today is talk about an invitation to what is happening here. Yeah. Okay, so it's not about telling all about category theory, which is in some sense it is impossible to talk about category theory, but the purpose of this talk is more generic in the more broad overview point of view, in the sense that how category theory actually appears in mathematics in the context, and how it influenced mathematics over all these years. A little bit of different structures in mathematics, where category theory plays a significant role, how it gives new kind of theories, how it is related with the existing set theoretic ideas, and at the end some important references for these applications of the category theory. So I will try to minimize this mathematical language as much as possible. And of course, very few things will be defined explicitly in a mathematical way. Is my screen is sharing, Zurab?
Yes, it is.
Yeah,
yes,
okay, sure. Thank you. Okay, so the idea is to give an intuitive idea of what is happening here, such that if somebody is interested who is not working with category theory or not using category theory in your personal research area, then always one can go through these numerous books and literatures and can come up with that. So let's start with the beginning. Now something is. Okay, here we see a picture of a pile of books, and it is literally impossible that if we wanted to find a specific book from this whole pile, it would take huge amount of time. and it's extremely disorganized, but definitely one can tell, a bookstore can tell, okay, if you wanted to find, for example, Feynman's lectures on physics, it is here. But since it's very much disorganized or unorganized, it is literally impossible to find in which side of this pile we have that book. So if we wanted to put this pile of the books, which is complete chaos, in a proper arrangement, then what we generally see a library does, they first not try to find a specific book, but they arrange the books according to the subjects. So for example, we put all the books in music in one pile, we put all the books in physics in another pile, and so on. And then what we get the shelves in library. So, and then we see something called the call number, which generally appears on the side of these shelves. And actually, each of these call number is unique with respect to some subject. So once we know that which call number is responding for the which subject, then we can directly go to that place of the library, and then we can go for the specific books of that. So once we are in a specific floor, say for example in a floor where the physics books are there, then we know that which shelves actually contains the physics book. Then if we wanted to go a specific book, say in gravitation or in mathematics in algebra, then there are specific call numbers, and then we go to the corresponding shelves and exactly look for that call number, and then we explicitly go to that corresponding place and we find exactly the book what we wanted to get. So from these three pictures, we see there is some kind of level of arrangements. So what we actually getting is, first we had done some organized information or the organized data, completely unorganized data. And then we organize them in a macro level, in the sense that we didn't literally pick up a specific book and put it on the shelf, but we actually organized in a more broad sense with respect to the subject, instead of going inside the subject and sub-classify within the subject by their sub-subject areas. And once we organize them with the subject, then inside the subject, then we reorganize with the sub-subject. So that third level of these organizations we can think as a micro level of arrangement. So taking these very simple examples from the real life, we can actually abstract it in a more general setup. So we can have unstructured information or unstructured data. And from there, we can try to find some structure between this data and construct some structures first, and then find some interrelation between the structures. And once we get these ideas between the structures and their individual structures, then we can always focus within a structure and try to understand the structure, one specific structure, in a more detailed way, just like this specific bookshelf where maybe we get all the algebra books or all books in optics. But that's actually this third part is we can see in comparison with this last level of these organizations of the bookshelf, which is the micro level. Now, with respect to this category theory, very roughly speaking, we can actually think this whole development of mathematics in three phases. One is before set theory, which we can call it classical mathematics. Then after set theory, we can call it set theoretic mathematics. And then what we get, the next level is what we call category theoretic way of looking at mathematics. So of course, since we have been already for a long time using set theory, that we do not feel the purpose of set theory or the significance of set theory, because it's so much amalgamated in our daily life when we do mathematics. We do not feel how complicated will it be our life if we do not have set theory and try to do mathematics. And once we have set theory, then we have different mathematical structures which mathematicians always working with, also physicists and other sciences working with, like groups, like Hilbert spaces. And each of these structure itself, when you study in a so-called micro level, we get lots of properties out of it. And we develop a theories of it. For example, we have group theory, we have ring theory, we have theory of Banach spaces, we have theory of Hilbert spaces, we have theory of topological spaces. Now, the question is, when you consider all these theories, then the theory of all these theories is nothing but, in some sense, the category theory. So category theory one can think as the next level of looking mathematics, which actually allow us to consider these different theories, or rather different mathematical structure, as one theory and studying them in an unified fashion. So since this talk is about category theory, let us see who are the people who actually first came up with this discovery or the idea. There were two people, one was Saunders Maclean and then Samuel Eilenberg, and they had a long collaborations, more than 15 papers, and it's actually the paper in 1945 where this general theory of natural equivalences in some sense gave birth of this category theory, so-called formally. Of course, this idea of category theory was before that time as well in a different form, Noethers and other people as well. And after this paper, there are lots of applications happened since then today in different fields of mathematics as well as in outside mathematics like computer science. We will talk about later on about that. Since the discovery of category theory, plenty of papers have been written, many textbooks of different levels of difficulties, challenges have been also written, but still people considered Maclean's own written book, Categories for Working Mathematicians, is classic and so-called the best, because it gives the good reflections of this theory in the context of mathematics. So this is very interesting just to see how Maclean and Eilenberg actually came up with this collaborative idea. Let's see what Maclean is saying in an interview in 1989. In the spring of 1941, Michigan invited me to give a series of 5 or 6 lectures. So I talked about group extensions. This was a subject on which I have done some work, and it came out of my earlier work on valuations with Schilling. I have calculated a particular group of extensions of p-adic solenoids. Eilenberg was in the audience, except at the last lecture, and made me give the last lecture to him ahead of time. Then he said, well, now the calculation smells like something we do in the topology in a paper of Steenron. So we stayed up all night trying to figure out what the connections was, and we discovered one. We wrote our first joint paper on group extensions in homology, which exploited precisely that connection. It so happened that this was a time when more sophisticated algebraic techniques were coming into algebraic topology. Sammy, which is Samuel Eilenberg, knew much more than I did about the topological background, but I knew more about algebraic techniques and that had practiced it elaborate algebraic calculations. So our talents fitted together. That's how our collaborations got started, and so it went on for 15 major papers. So initially, although the collaboration actually started with respect to this algebraic topology or the development of the algebraic topology with these two eminent mathematicians coming from algebraic and topological background, but eventually that's landed to the birth of this theory of categories. Okay, so this is the little bit of history about the starting point of these people. And before we talk about category theory, let's start to see what it is all about. But before doing so, let's start with some structures, which is actually the main thing what we started with category theory. So there are two things. One is sets and set with structures. So before we give mathematical examples of sets and sets with structures, let us try to understand this concept of sets in a more intuitive or more realistic way. Don't be scared. It's just a picture of a skeleton. Okay, very good. So skeleton is made of bones. So we understand calcium, etc., etc. But definitely all of you agree that if we add something with it, then we get this so-called the body of a human being. So if we think the skeleton as, for example, set, then if we put some biological entities, biological things like flesh, blood, bone marrow, and other things, which all biological people understand better, then we get something more than that. So we can think that if we think the skeleton as a set, then the structure we put on the set of this skeleton. Let us take another different example. Imagine we have on the top, we have an empty drawing room. So think it as a set. And of course, we can furnish by interior decorations, putting our chairs, tables, we can paint the walls, the wall hangings, and many other things. So when we have this empty room, we put something top of it, in the sense we add something with it, and then we get something along with it. So one thing we notice between these two pictures, which is common, that to put or to define or to have structure, we need something at the very beginning on which we actually do the structure or put the structure or implement the structure. So in some sense, if there is some basic things which is given to us and then we define something or we add something on top of it, satisfy something, then that intuitively can be considered as a structure on that set. Now let us take some very, very simple examples of mathematical structure. So as a set, let's just say take this set of integers, and then we just take the addition as an operation. When we add 2 plus 3, that addition. And then let us consider another different set of non-zero real numbers, but we now change our operation. Now we take the simple multiplication, like 2 times 3, 6, that kind of multiplication. Now let's take another different set, completely different, the set of all n by n invertible matrices over, say, real numbers. And then we define another matrix multiplication, which we already know from our linear algebra undergraduate courses. We can take also a geometric example, like if we have a, say, equilateral triangle, and if we wanted to move the equilateral triangle such a way, either rotating or reflecting, such that if I do that changes, but I cannot recognize the changes actually happen because it should come back to the same places. So what is happening here, if we consider these things written in blue as sets and the things written in red, then these two are different entities in some sense. Now we can only consider these operations on these sets, or we can consider some extra properties these operation satisfies on these sets. So whether which kind of properties we actually adding, or even if we do not add any kind of property, still it gives a structure on the set of integers with addition. And if we have only such addition, then it has a name which is called magma, but we don't need to worry about this technical name, because for intuitive understanding of this, we actually don't need to go through such details. But if we have some additional properties, like addition satisfies some kind of associativity, if it is familiar to you, and there is some unique integer like 0, when we add with any integers, we get back that integer. And we know that if we, for any integers, there is another integer. When we add these two integers, we always get 0. So if these kind of properties are satisfied, then basically we get a specific mathematical structure, which is called group. So group is nothing but a set with an operation, and we get some extra properties satisfying these examples. So this is one specific type of structures. I mean, all these 4 examples where we have sets and we have operations, and these operations may satisfy some extra properties, and according to the properties what it satisfies, it gives the corresponding mathematical structure. But we can actually impose a mathematical structure in a very, very different way. For example, let's take set of 4 elements A, B, C, D. Then we can take some subsets, some specific type of subsets, which is written on this red color on the right hand side. Of course, we didn't choose this set of subsets randomly. They satisfy certain properties. And if this certain properties is very specific, then what we get actually is something called a topological structure, which we actually use in a very different areas of mathematics, as well as definitely in physics, because when you consider manifolds, that's nothing but a special type of topological structure, again with one additional some other structures, like a differentiable structures. So topological structure is another example where the structure is not as the same nature as the previous 4 examples. And here the structure is determined by certain kind of subsets satisfying some properties on this set. And one naturally can ask, can I have different structures on the same set? In this sense, of course, we can have same sets, and it is amazing to count it out that there could be 355 topological structures on these 4 element sets. So depending on the choices of these subsets satisfying certain properties, all of them, then we can get these different structures. So intuitively now we understood there is a set with structures, and such examples are like topological spaces is a structure, is a mathematical structure. Group is a mathematical structure. Even we can only consider set with the operation that's in a mathematical structure called magma. So once we get little bit idea, then the next question is, we wanted to understand the preservation of the structure. So if we have two different structures and we have a map or a function between them, then it preserves the structure. Now, what does it mean by preserve structure? So let us go back to our undergraduate calculus, or maybe in high school, but we don't write log as a formula. Of course, we write the formula on the right hand side always, but we do not consider in general in calculus as a function, this log as a function. So if we take these real positive real numbers with multiplication on the left hand side, and if we take the real numbers with addition on the right hand side, actually, then logarithm actually telling this well-known formula that it preserves the operation. The operation on the left hand side is actually preserved by these operations on the right hand side. So this pictorial description actually telling that if we take two elements, x and y, and first we multiply them, and if we take their image, and if I first take the image of x and image of y, and then if we do the addition, they actually essentially the same thing. So this is a typical example of the preservations of a structure. But as we see that structure can come in a different way, and groups and structure is one way, but the another one was topological spaces. Another very simple undergraduate structure preservation comes in continuity. And many of us have the privilege to teach calculus, and we always notice that epsilon delta definition of limit and continuity getting a nightmare for students. Who is epsilon, who is delta? I mean, for FG epsilon, there is a delta, and it's a complete mess. And this is one of the questions every student try to avoid, at least what I experienced in all these years of teaching. And one of the reason is that, of course, there is a technical part of this epsilon delta, which is actually sometimes could be very technical to find delta for a given epsilon. But intuitively, one can understand what is happening if we take a real valued continuous function. So what it does, this continuous function, is actually preserves also structure. But what is the structure here? Here, preservation of structure means the preservation of the distance, the nearness. And that's exactly what this epsilon delta so-called definitions, or the more general definition of a continuous functions for a topological space, actually telling us that when you wanted to preserve the nearness on the left-hand side of your functions on the domain side, and if it is continuous function, then it should preserve the distance. So epsilon delta definitions is actually telling nothing but the continuous functions definition, that it preserves the distance function. And that's actually another examples of preservations of structures in the sense of continuity. So let's now take some examples of mathematical structures and their corresponding structure preserving functions. Do not worry about the first column. This will be immediately clear in the next slide. So if we take our objects as sets, like our integers, like positive reals as we discussed before, then its structure preserving functions is functions. Then you may ask, wait a minute, what it preserves? It doesn't preserve anything because it doesn't have any structure. So functions itself is not functions problem that it doesn't preserve anything, because it has nothing to preserve there. But if you have a little bit more, then it preserves. For example, if you have groups as our object, then what is preserved? It preserves these binary operations, and we all know, those who know about this group theory, that it preserves these binary operations. And hence, actually, we actually also prove that it preserves identity, preserves inverses, and other things. So if we consider our sets with the structure as groups, then the structure preserving functions will be this group homomorphism. Then let's go to the linear algebra. If we have vector spaces, then what will be the structure preserving functions? It will be the linear transformations. And if we take metric spaces, here we can take different classes of functions as our structure preserving functions. For example, we can take non-expensive functions. If we have topological spaces, so the heart of topological spaces is about continuous functions, so it preserves this nearness. We'll be lucky to preserve distances if we have this metric. And again, as we said, that on the same objects, we can consider different structure preserving maps. For example, on the same topological spaces, we can consider homotopy classes of functions. And this is nothing but essentially the subject area of algebraic topology. And then you can consider uniform spaces, where uniformly continuous functions will be the structure preserving functions. If we go to function analysis, then we can consider Banach spaces. Then we can consider bounded linear functions. Or if we consider general topological vector spaces, then it will be linear continuous functions. And it is very easy to see why it should be linear continuous functions, because when you say topological vector spaces, so it has two structures. One is vector space structure and this topological structure. Now let's see, in vector space, we have linear transformation. For topological space, we have continuous functions. But if we put these two structures on the left-hand side, we should also put these conservations of this, or preservation of the right-hand side. So it should be linear transformation as well as continuous functions. And that's why for a general topological vector spaces, the structure preserving maps naturally should be linear continuous functions. And then we can consider differentiable manifolds. Then we can consider smooth functions, infinitely differentiable functions. We can have different natures of structures like posets. We can consider monotone functions. And we can have Lie groups. And in that case, it should have smooth group homomorphisms. And again, why should it be smooth group homomorphism? Because it has two pieces. One is Lie and groups. Of course, Lie means it's actually talking about on a differentiable manifold. When you put a group structure on a differentiable manifold, then we get this Lie group. Group structure on a differentiable manifold. And only differentiable manifold, we already have the smooth functions, and group has group homomorphism. So obviously for Lie groups, our structure preserving map should be of the kind of smooth group homomorphism. So here we have varieties of examples from different areas of mathematics where we have these objects, which are the structures, mathematical structure, and their corresponding structure preserving function. So having these examples, now let us see what is actually category. So category essentially has 4 data. One is we have something, a collection called objects. We are not going to these technical things of large, small, and everything. Accordingly, we have this thing because that's not so needed at this context. And then the other thing is that for every 2 objects, we have a set of objects, which is called morphisms. This set could be also empty. Not necessarily that we always have a map or an arrow between them. So this is another set of things what we need. And then for each object, we associate one specific type of structure preserving map, which is this identity morphism, and that should be added with every object in our collection of objects. And then whenever the second object of the this class of morphisms coincides with the first object of the second map of the morphism G, then we must be able to compose them. So the composite of the G and F should be in our collection. And once we have these 4 data, then these 4 data must satisfy 2 identities, such that it is very simple, like when we consider this 0 in a group, that when we add any number with 0, we get back that 0. So you can think like that way, that when you compose any morphism with this identity morphism, we must get back the original morphism, either on the left-hand side or on the right-hand side, in the sense of the domain and the codomain of the morphism F. And the other thing is, which is very natural, that this composition of this morphism must be associated. So this is all about the definition of a category. So it is simple to see that all these previous examples, what we considered, actually each of them an example of a category. And then on the first column, where we actually showed this specific notation to denote this category. So that means this all group, so this group homomorphism actually forms a category. Then this smooth manifolds forms a category, Banach spaces forms a category, topological spaces forms a category. So in some sense, whatever the mathematical structure we deals with essentially is an example of a category. So once we get this specific definition of a category, so we got some countries. Now we wanted to connect 2 countries. That means we wanted to find the relations between 2 categories. okay, what is happening? So this is a picture which I found a bridge between France and Germany. I never been to this place, but maybe some of you are already familiar with this bridge or maybe passed through this bridge. So I suppose that one side of the bridge is France and another side of the bridge is the Germany. So if you think the France has one category and the Germany is another category, then there is bridge. What is doing? It's actually connecting these two things. And once we get two categories, we wanted to connect them to understand the relationship between them. And since if we construct a bridge and if we allow people to pass from France to Germany or Germany to France, of course, there should some rules need to be satisfied to pass. You cannot just cross one country to another, I suppose. And similarly, when you have two categories, then we are expecting that if we have such kind of connections between two categories, that's what is called functor. That means it's a function between the two categories in some sense. So first we consider the functions of morphisms between two objects of a category. Now we are going to the second level where we have two categories. Now we have to connect them. And that type of functions is called a functor. So before we actually give more concrete examples, let's see an example which comes very naturally from our previous example. We all know that we tell students, how can you forget this definition? How can you forget this proof? So sometimes forgetting is prohibited, and we actually warn them you shouldn't forget. But we are very thankful that we are happy today because we can forget many things. We cannot remember. If we imagine that we remember everything, then our life could be terrible, and we cannot think properly. So forgetting is good. And is it also good for mathematics? Yes, it's also good for mathematics because it gives a functor. Okay, let's see how we can get it. Remember that we had a group structure or some monoid structure only Z with an addition. And then let's forget the structure, which was coming with this addition and maybe some extra properties, and just get back only the original set. Okay, so we had group or set with structure. We forget the structure. We landed up with only the set. Then we had another structure, which was a real positive real numbers with structure of multiplication, possibly satisfying some extra properties. Forget about the structure, get back the corresponding set. By the way, these sets are called underlying sets because that was with attached with it. And the third was all those invertible matrices. We had this matrix multiplication. Let's forget the structure, and we get this only the set of invertible matrices. So what is happening? On the left-hand side, we had all different types of groups. And on the right-hand side of these columns, we have the corresponding sets. And what's the difference between the left-hand columns and the left column and the right column? Left column was in some sense more rich, in the sense it has a structure. We set along with the structure. And unfortunately, it forgets the structure. And what is a bare set is there. So what is actually giving? So you can consider this category of groups, where we consider all groups, and then forget the about group. And if you forget the group, what left is nothing but the sets. And this, since it's forget it, its name is also called a forgetful functor. Okay. Now, we do not telling it and details before the definition of a functor, but let's take some examples of this kind of functor. Okay, first, let's take the definition also. So imagine that we have two categories, C and D, and F will be called a functor. Whenever we have, say, objects C, C prime, C double prime, all these are objects of this category on the left-hand side C, and then we take their images, which is this FC, FC prime, SC double prime, and we compose them, as we said, as in the category, as long as the C prime matches with the F and G, then we must have G compose F, and similarly on the right-hand side, we should be able to compose. And of course, by the definition of a category, you must be able to add an additional morphisms of this identity with each of these objects. Of course, here we only drew one of this identity morphism, but of course, it is assumed that it is also with the C prime and C double prime similarly on the right-hand side. And to get this so-called the bridge between France and Germany, or between two categories C and D, it must satisfy the property that the image of this identity morphism of this one C attached with the object C must be actually mapped to the corresponding identity morphism of the image of C. And the other thing is that it preserves so-called this composition in the sense that if we have G compose F, and if we take the image of that individually, then their composition must actually map to the composition of the other thing. So once we have these conditions satisfied, then what we get, nothing but a definition of a functor. So as long as we get two categories and we can define such a function in this manner, then we always can consider functors. Okay, so now let us take some examples in mathematics, some very crucial examples which actually determine some areas of mathematics in past and as well as in current state. Very simple example of a functor is this power set functor. We always ask students to find the power set of a given set, but what we actually asking actually whenever a set is given, when you consider set of subsets, look at what we are saying. We are saying set of subsets, which is again a set. So for each set X, we actually consider set of subsets of that set. And when you have a map between two sets, X and Y, on the left-hand side of this mathcal P, then there are images also that gives the corresponding maps on the other side, and actually satisfying these conditions of this functor. So this is one of the simplest example of a functor, which is this something called power set functor. Now let's take an example from another field, which actually one of the birthplace of the category theory by Samuel Eilenberg and Saunders Maclean, which is algebraic topology. So very roughly speaking, what we are doing in algebraic topology, if we have two different topological spaces and we wanted to understand whether they are topologically equivalent or not. Now, very soon it was historically understood that trying to find up to equivalence up to homeomorphism is actually hopeless, and rather we need to go up to homotopies. But don't need to worry about this general notion of homotopy, but it's assumed that it's more weaker version than homeomorphism. But still, the problem is not simple actually to see whether two topological space are same in some sense. So what we are doing actually, given a topological space X, we associate a group structure. And then given a topological space Y, we associate another group structure. But the magic is that if these two group structures are not same in the sense of group isomorphism, then these topological spaces will not be same. But what we are actually doing here, we are actually considering several topological spaces and hence and continuous maps between them. So basically, this is nothing but category of topological spaces. And on the right hand side, these attached groups is actually abelian groups. So it's a special type of groups where your multiplication is commutative. That means A times B is B times A. The times can be any kind of operations. So what we are actually doing, we are in algebraic topology considering different kinds of functors from this category of topological spaces with these homotopy maps, morphisms, and then other side we consider these groups and there's group homomorphism. So these associations of these homology groups is actually can be represented as a functor. Now from algebraic topology, let's go to another field of mathematics, which is algebraic geometry. And in the sense of Alexander Grothendieck's work, algebraic topology is essentially nothing but a study of functors. But how can it be? And this is one of the very crucial landmark of Grothendieck's work, which make a big revolution in the following sense that before Grothendieck, initially when we try to solve the polynomial equations and try to see their geometric pictures, the solutions were taking over the reals in the field of reals. Then immediately people understood this is a very restrictive version, so let us go to the complex numbers. And then it will generalize to the field. But it was around that type of generalizations. So what Grothendieck did, Grothendieck said, actually change the whole philosophy. It's other way around. He actually starts with any ring, and out of that ring construct a geometric object, which is called affine scheme. So what is actually happening, if you take any ring, for example, a ring of integers is an example of a ring. Of course, every field also a ring. And then you take the corresponding something called prime ideal, and you put extra structures, consider some kind of topology on it, some sheaf structure, etc., and then you actually basically get a geometric structure. And essentially, whole algebraic geometry, as Grothendieck mentioned in his EGA 1 on the second version, that in this way to see algebraic geometry is nothing but study of the functor, which is he called a spec functor, because it is essentially a functor which taking as a ring and then take the image as the corresponding set of prime ideals. And of course, this make a huge impact on algebraic geometry from this understanding point of view, but it gives a big influence on this number theory. For example, without this idea of Grothendieck, it was not possible to use algebraic geometry tool in number theory. And one of the major things is that in improving well conjecture, which done by his student Delin, actually used quite a lot of this idea of the Grothendieck. And of course, the proof of Fermat's last theorem also used quite a lot of these tools from this algebraic geometry. And as we see, this possibility of using algebraic geometry tools in the case of number theory was possible because of this generalization from the reals to integers. So integers was nothing to do with the field, and it's actually an example of a ring. And this approach of doing algebraic geometry unify, or in some sense help to use the tools of one area of mathematics to solve problem, which is an unthinkably complicated problem of Fermat's last theorem, in completely different area of mathematics, which is called number theory. So here are some examples of functors from different areas. Now let us see how, if we think categorically, how we can actually unify different mathematical structures or see similar structures in one platform. So here is one typical example. So let's start with group. So what is a group? Okay, group is nothing but again an algebraic structure where G is a set, 3 operations. Okay, first operation is the binary operation, and generally what is written on the red color, that's exactly how we teach in our undergraduate level. What I wrote on the left hand side is nothing but in a more very specific way, because when we say B and C, we actually put in operations between B and C. That has been written as MBC. Once we get BC, then we apply M again and put BC together with A, and that's why you get M of A of M of B or C. So this is the binary operation which satisfies this associative property. And then when we say there exists an unique element identity, of course that unique element can be thought as a nullity operation. What is a nullity operation? Is nothing but from a singleton set to that G, and that's nothing but picking up an element. So we can think the image of this function as itself the element key, and then it satisfies some identity, which we generally write as we wrote in this red color on the right hand side. And then we get this inverse operations, and once we have this, we get groups. But wait a minute, this is a group on a set, because you see, for the first thing what we said here, actually G is a set. But in different areas of mathematics, we heard the word group, but associated with some other words with it. Okay, so before we go that, let's take this example. What's different here? The containers are different, their sizes are different, their shapes are different. But what is same here? All the containers contain the same content. So let us take its water. So we can think water as one content putting in different containers. And of course, the shape of the water will be different depending on the shape of the container. And this is nothing new to us. I mean, we all know it looks like this, but in mathematics, we also get the same thing. For example, if we take sets, then we have group structure. As usual, we teach in undergraduate. If we take group, and then if we consider group on a group structure, then we get actually abelian group. Then topological group, that means if we take our original structure as topological space, that means our container as topological space, and our water, we put the same water, and the water is our group. So in first case, the set is one container, we have the group structure. Then the second container is group, we put the group structure, but it looks different, it is abelian group. Then third container is topological spaces, we put the group structure, we get topological group. If we have C infinity manifold, then we put the group structure, we get Lie groups. So, and then if we take algebraic varieties, which is a special case of affine schemes in the case of algebraic geometry, and then we get another type of groups, but it's called algebraic groups. So the advantage of looking all these things categorically, which is a technical term in categorical terminology, is called group object. That means you take different categories and you construct or you consider the group structure on this, and then you can actually see how these groups are interrelated, in that sense that the same group structure we define, only our categories are different, only the mathematical structures are different. Okay, so with that examples, let's see that already we have seen that in different mathematical structures, in different areas of mathematics, category theory actually comes naturally with examples: algebraic topology, algebraic geometry, and algebra topology itself. But category, before we go category theory, let's see what we today is using actually axiomatic set theory. So all this mathematical structure or the properties what we study about mathematical structure, essentially based on some axioms on sets, and these are done by varieties of people: Dedekind, Cantor, Zarmilo, Frankel, and others. So we actually started with a set of axioms, and based on that we develop all mathematics. What do we actually get? First we define natural numbers, integers, other number systems, then complicated group structure, more complicated structure, manifold, Banach spaces, everything. But our starting point is set of axioms. That similar way, there are developments of the category theory from this axiomatic point of view. So we can start with different set of axioms, categorical way, and then try to see which mathematical structure we can unify them and can study them together. So from that point of view, one of the very first one was abelian categories. It's a certain kind of categories in the sense that categories which satisfy some properties or some axioms. Saunders, Maclean, Buschenbaum, Alexander Grothendieck, these are the people who came up with this setup with these axioms. And then we had these Quillen exact categories. Is actually essentially Yoneda first came up with this idea. Then later on it's also used and further developed by Daniel Quillen. So this is another class of axioms and another axiomatic way of category theory. Then we have Michael Barr came up with these Barr exact categories. Then another set of axioms for category is the protomodular category due to Dominic Bourne. Then we have semi-abelian category by George Anneliese, Markey, Walter Tholen. Then we have Marco Grandis came up with another set of axioms, which is called Grandis exact categories. And then we have Noetherian forms, which actually Zurab Anneliese came up with along with students and collaborator. By the way, those who are not familiar with category theory or not known to South African or mathematicians, G. Anneliese and J. Anneliese is not a printing mistake. George Anneliese is father of Zurab Anneliese. So both of them are attached with different set of axiomatic category which they come up with. So these are the development of the category theory itself as a language, and it develops as a category theory and try to implement to understand different mathematical structures. So saying so, let's wrap it up with some questions and answers, which generally everybody asks when somebody sees some new language or some absolutely new things. So what category theory does in mathematics? That's a very, very natural question everybody asks. I myself also asked at the very beginning. Well, category theory gives a way to unify mathematics and clarify mathematical concepts. And it helps to prove, becomes simpler. For example, if you wanted to prove higher dimensional Brouwer fixed point theory, then if we use categorical language, believe me, the proof will be much simpler than the traditional way because it's checking some kind of functoriality. It is easier to find connection between different mathematical structures and mathematical notions because this is one of the main specialty of category theory, which helps us to understand considering different mathematical structures together. And this is one of the very, very novelty of the category theory, which is not quite possible from the set theoretic point of view. And allows to formulate a specific mathematical notion for many mathematical structures. So it can extract the essential component of a notion and generalize it and study it on the same thing for different mathematical structures. So categorical tools actually help us to do that thing. And finally, as we mentioned in those axiomatic setups, that it develops new theories because since it gives another language, that language when develops automatically develops new theories. And as we mentioned at the very beginning, that category theory in some sense is the theory of theories. So if that theory develops, of course, it actually gives more information about the original theories like group theory, theory of topological spaces, etc. Next, very, very aggressive questions can come. Can category theory solve Riemann hypothesis? Most probably not, because that's in some sense at this moment, or not in general, the purpose of the category theory. Because even we can ask, can set theory help me to find 2 plus 3? Absolutely not. 2 plus 3 in that sense, how much I use axioms, it will be much easier to do it not that way. But the purpose of this is to get a clarification and to understand the structures, to understand the relation between the structure. So it may be possible that if we can give a general, much more generalized formulations of so-called one of the unsolved problems or Riemann hypothesis, then it leads to better understanding of the problem, because it's the same thing actually happened with well conjecture. When Grothendieck picked it up and what Deligne proved it's absolutely different formulations compared to that. Similarly, the Fermat's last theorem, the statement of it, even a high school student can understand. But the proof, of course, I do not understand the proof, and very few people actually in the world all completely understand the proof of Andrew Wiles, which is more than 100 pages. The point is that sometimes the problem is very simple in the sense of descriptions or formulations, but to solve the problems, we need more machinery, more heavy machinery, or better clarification of the problem. So from that point of view, category theory may help actually to get understanding. Once you get a better understanding of the problem itself than the solving the problem itself. And then can you have applications of category theory in other fields? It depends. First, we should be able to formulate the phenomena, whatever the area in science and in the real world we wanted to apply category theory, because we remember that we first need to form a category, whatever the phenomena of the problem is. And the last 2 days, actually, Zurab and I was trying to doing some kind of experiment, taking a real phenomena and try to see whether can we construct a category. And once we manage to construct a category, then studying categorical properties may give some better understanding of the problem from a broad perspective. And that may give a clue that which way, if we go, we can get a better picture of it. Saying so, here are some standard references of in mathematics, different areas of mathematics where things are done more categorically or using categorical language. Of course, for the best suggestion for reference for the algebraic geometry is Grothendieck's own work, because Grothendieck is the person who introduced category theory in algebraic geometry. Hurston's book is the most used textbook in algebraic geometry all over the world. Then there is another book, Gorge and Oldham. Then algebraic groups or Lie groups, De Mazud and Gabriel. Gabriel, by the way, was a former PhD student of Grothendieck as well. There is another very elaborative lecture notes by John Milne. Then there is a textbook of Waterhouse for topological groups with a categorical flavor, or categorical approach is Struppel. Then for shift theory, of course, Maclaurin's Mordek's book is one of the classic. And for algebraic topology, Spanier is always considered classic, and there is a more recent one published by European Mathematical Society by in algebraic topology. And here are some references which I actually came across, but I completely like to leave it with the corresponding specialist in the respective areas to determine or decide how much category theory can really help to solve their problem or to formulate their problem. Of course, it could be a collaborative work between a mathematician and a physicist or a computer scientist or a biologist, but the specialist knowledge is very much needed to understand whether it's really helping these tools or not. So in that case, for computer science, of course, Eilenberg himself wrote 2 volumes book on automata, languages, and machines, the same Samuel Eilenberg. Then Miloski, very recent book he actually published, and he actually, in preface, in some sense, he actually warned people that current programming is not based on a very, very solid foundation. And before it completely collapses, because of the high demand of different critical situations, we must rethink of the foundations. And that's why he also thinks that category theory can make a very big impact on the foundations of these programming languages. Then there is a conference proceedings edited by Manes. Then in physics, there is a edited books of the papers on new structures of physics. Then category for quantum theory. Another is picturing quantum processes. This is has lots of pictures, more than 800 pages book, and is very lucidly written to read. In biological science, there are books on these brain science in the cognitive way. And then Arishman, along with others, we have this paper which actually relate also with mathematical statistics. And Arashman is one of the category theorists, and his wife also recently wrote another book, and which actually gives a lots of applications of category theory with respect to this biological science, or more with this cognitive science. And generally speaking, there are two books written by Spivak, which actually in some sense applied category theory. And the advantage of these two books that you do not as such need to consult another category theory book to understand category theory, but he tried to explain everything as much as possible with rigor, but he explained that it is not as rigor as it should be, but gives quite a lot of applications of it. Maybe Zurab, do I have time or probably not, right?
I think we're almost at the end in some sense.
Yeah, okay. No, then I think let me stop here and say thank you to all of you.
Yeah, thank you very much, Amartya. That was a great talk, a fantastic introduction to the ideas and concepts and potential applications of category theory. Thank you very much.
Thank you.
I would now like to, pleasure, ask Zurab if we have already some questions in our Q&A. And if not, I would like to encourage our participants to raise their hand and maybe ask a question in person, please.
I have been answering some questions on the chat, so all of them are answered at this stage, and there is nothing on the Q&A.
Thank you so much, Zurab.
Thank you. Let's see. Here, sorry, there is a question coming. Voila. Maybe Partha would like to ask a question in person. Yeah.
Can I be heard?
Yes,
yes,
please.
we can hear you.
I'm not sure if I missed it, but did you mention topos theory also?
No, I didn't mention. Yes, that's another area, definitely.
Because topos theory and homological algebra were more or less contenders. So abelian categories and topos theory, initially, that was the highlight of category theory.
Yeah, definitely. Thank you. Thank you for addition. Yes, definitely.
I think it was mentioned, in fact, because you did mention MacLean and Mordak's book.
Yeah, shift theory, but not explicitly toposes. Yes.
Book is about toposes. So, yeah.
Yes, yes, of course. That book is about toposes. Partha, you have another question?
No. I did lower
okay.
my hand.
Okay. No,
Okay. Let's see. And maybe I can ask a question, Amartya.
Yes, please. Yes, please.
You mentioned a few books and a few papers and so on and so forth. For an absolute beginner, what book would you recommend?
You mean to apply category theory in other fields or just to learn category theory?
Yeah, a little bit of both. Yeah.
Spivak's book is good in the sense that it has lots of examples. Of course, if one can always argue that MacLean's book is the best, of course, there is no doubt about that. But it depends on the taste, on the person, what approach you like to do. But to me, I found that Spivak's book gives much faster way to allow you to reach, to think about applications to other fields. But that's absolutely my opinion. Of course, another person can differ from that.
Okay.
Thank you very much. May I contribute to an answer to this question?
Please.
So my impression is, especially now in preparation for the mini school, I've been looking a lot, and my impression is that in modern science, we very much very quickly start to use technical language to explain even basic things, and I think it's the same with category theory. Even Spivak's book, I think it's too much mathematical language for someone who didn't have proper mathematical, postgraduate mathematical training, specializing in certain specific areas, it's difficult to get past through the barrier of the language. I think the language issue is significant. I've been trying to understand some ideas of modern physics from various sources, and it's the same problem. So either it's too vague, the explanations, or it's too technical. So there seems to be that the middle ground is difficult to find, and certainly for category theory resources, unfortunately, it's also the case.
Okay. Okay. Thank you. Thank you very much. Are there more questions? There doesn't seem to be. I think our participants are a little bit shy this afternoon. Let's see. If not, what we can do, since we announced that we want to have again a virtual social interaction in Kumo space, and the link I posted, you will find it at the beginning of the chat. I think I posted it. Maybe I can quickly post it. Ah, yes, it's still there. Yeah. No, sorry, I sent it only to the panelists. Sorry. Let me send it to everybody. So here we go. Voila. That's the address where I just shared the link where we will have our virtual get together. And Amartya and Zureb, I hope will join us there. So maybe you will be able to interact with them and ask more questions in maybe a less intimidating setup that is not so formal. And if you join us, you will see we will also offer you drinks at no cost. They are virtual, of course, but so there are some benefits in joining us just now. And if everything went according to plan, the website of the social should have opened after you opened the Zoom call, yeah, in your browser. So you should find it very easily. If not, just type in, copy and paste the link from the chat, and we will see you there in a couple of minutes. Yeah? So Amartya, thank you so much for a very nice talk. It was really inspirational. I will definitely look into some of the books that you recommended, and maybe we can develop the middle ground.
Yes, maybe.
As a project, yeah, because that would be very useful probably for many people. Yeah. And Zurab, thank you very much for your assistance with the questions and for taking care of the chat so nice. And Ilya, thank you for being there as usual. So thank you very much again, everyone. I'm looking forward to see you in a few minutes in another virtual environment to socialize a little bit. Yeah. So thank you very much. Have a good afternoon. Thank you. Thank you very much.
Thank you. Bye.
Thank you very much.